Good morning. Oh, yeah, it works. Perfect.
Peut-être qu'on peut le mettre plus proche dessous. Si tu le pinces ici, peut-être au centre.
Ça va être trop fort après.
Ah, ça serait fort. Ok.
Je vais parler fort dans le micro. Hein. Comme ça? Ouais, c'est bon. Please, I get the stage like this. Well, thank you very much for all being there. I'm very glad. That's my first time in Brazil. I'm impressed. I must say, it's a very large city. So I did my PhD in Paris, which was the largest city for me so far. And I must say, Sao Paulo is it's a bit larger. So right after my PhD, I actually moved to Hamburg, the University of Hamburg, in the northern part of Germany. It's also quite a big city in Germany. It's the second largest after Berlin. And well, since that time I'm there. It's a long time ago now, roughly 7 years. It's a pleasure for me. I will try to give a nice lecture on optical lattices and artificial gauge potential. So if you don't know yet what it is, don't worry. That's the aim of this lecture, that you understand what it is about. Of course, in the frame of 3 lectures of 1 hour and a half, it is impossible that I give you a complete overview of all the results that have been achieved working with optical lattices and ultra-cold gases. So it will be a biased overview. Of course, the thing I find nice and the focus we have in Hamburg will come first, just to let you know that it's too challenging otherwise. Everyone can hear me, understand? Excellent. Maybe I start to present a bit the activities in Hamburg, because it's always a nice time to start with advertisement, like all good films. So because we need motivated people always, so maybe you want to try Hamburg. And it's a very big center for quantum physics, so especially at the Institute for Laser Physics, there are now altogether 6 groups. 4 of them are experimental groups. The group of Roman Schnabel is working only with light, but quantum states of light, quantum optics. There are 3 groups for ultra-cold gases altogether. The group of Andreas Emmerich, they have 3 experiments there. The group of Henning Moritz, they have 2 experiments now, 2 setups for ultra-cold atoms. And the group of Klaus Engstock we're working in. There are 2 theory groups where we work very closely with them, Ludwig Mattei and the group of Peter Schmelcher, so it's a very nice place to be. I don't know whether the other speakers told you that already, but I love this field because theory and experiment really go hand in hand. So, and that's a strength, and you should use it. And that's very nice to have all these activities at one institute. So in the group of Klaus Engstock, so it's a big group here. You can see Klaus Engstock, if you don't know him yet. And we have 3 permanent scientists, Christoph Weitenberg, Christoph Becker, and myself. It's a new picture, I don't recognize our position yet. And you see there a bunch of people. That's because we have 6 projects all together. 6 experimental setups, so I'm in charge of 2 of them. That's nice and colorful picture. At the end of the lecture, I hope you understand what it's all about, and we can discuss about it, of course, in between. So the first project I'm working on is we work with ultra-cold atoms and optical lattices. Of course, they have not a cubic geometry, but an hexagonal geometry. And our aim, so with a condensate in optical lattices, I will present this today. You have this band structure. Usually, the condensate is sitting at the bottom, the lowest energy state. And we try to make more fancy states by exploring higher bands of these optical lattices. So this has been pioneered by Andreas Emmerich in Hamburg and inspired by this. We do it in our nice geometry where a lot of fancy states are expected to live. The second project I started now 4 years ago, so it's not yet on the website, so it's only here for you. It will go online as soon as the first papers are out, because it takes long to build such a quantum gas machine, so roughly 3 to 4 years. Now we are so far. So the idea is to combine ultra-fast and ultra-cold. So ultra-fast in form of ultra-short laser pulses, like 300 femtosecond, that we shine onto the condensate. The time scale of a femtosecond laser is not relevant for ultra-cold atoms dynamics, so it's usually much slower, like milliseconds, but it's actually a very nice tool to photoionize in a condensate. Locally, few atoms, a lot of atoms, and play actually with hybrid quantum system formed with ions and atoms. And the 4 other projects, so 2 of them are led by Christoph Weitenberg, together with Klaus Engstock, of course. One is also optical lattices. This I will present in my 3rd lecture, the results on the topological band structure. So now we can do fancy lattices that have topological properties. You will also understand more as it goes. A quantum gas microscope, that's also a great tool for optical lattices. I will present this in my 2nd lecture. And 2 projects led by Christoph Becker. Here you see as well, it's also about lattices. They work with ytterbium, which is very nice properties for precision spectroscopy. And in this quantum hybrid system, they're trying to couple a Bose-Einstein condensate with a nanomembrane. So the idea is these are 2 quantum mechanical systems. You can cool them with a ground state, try to make a cat states between a condensate and a nanomembrane. Also a very fancy project. So this is the 6 projects we have in Hamburg. We have, I don't know whether you have seen ultra-cold gas labs so far. Who didn't? Did you already see some pictures or some? Yeah, very nice. Okay, so I can skip the 2 next slides. That's the usual optical table with lasers we need for cooling and lots of further manipulation. We have, of course, vacuum system, and you have somewhere always a nice laser-cooled cloud of atoms to see. So here it's like a rubidium cloud, just to give you some few impression. Okay, now back to the lecture. What is the aim with the optical lattices and ultra-cold gases? So we don't only do it because it's fun. So there is an idea behind it. And the bottleneck comes from the theoretical solid-state physics. So they face the problem that model Hamiltonian cannot be solved. So I don't mean cannot be solved on a piece of paper, not even on a computer, because for such an Hamilton operator, this is called a Hubbard model Hamilton operator. I will derive it today. So just saying that your particle can hop from one side to the next and interact on site sounds simple, but this cannot be solved. And even not with computer, because even with for numerical simulation, it scales exponentially in size with the number of electrons involved in your problem, and state of the art is like 40 electrons. So it's really still far from real solid-state systems. And an idea that stems from Feynman in the 80s is to use actually quantum physics to solve the problem for you. And what we do in the lab is we try the best we can to build up some Hamilton operator that the theory colleagues from solid-state physics are interested in, and to implement it on the atom, let it evolve in time for a set of parameters, and eventually look at the ground state and try to be clever out of it. Find out which kind of state it is, which kind of properties it has, and so to reconstruct some phase diagram and help to know whether this model, for instance, supports superconductivity or not, which kind of minimal model you need for that. So that's the big aim. Good. I think that's more or less it. The structure of the lecture is very simple. I decided to break it in 3 parts. The first block is how we build up the Hamilton operator. Some introductory slides on optical lattices, how is it working with real atoms, so typically atom physics in that part. Then how we describe it for non-interacting properties. So this will remind you of your solid state lectures, Bloor theorem, all these things. Band structure, wave function, and get to the Hubbard model, describing the physics of these ultra-cold gases in the lattice. So this would be the harder part, not a lot, but for me, experimentalist, some theory. It's meant for the experimentalist among you. Never be afraid of writing up an Hamilton operator, diagonalize a matrix, so that helps to understand what's going on, and it's doable. The part 2 is addressed to the theoretician among you. It's a state of all what we can do with these quantum gases and optical lattices in terms of probing. How do we look at it? And that's important for a theoretician to know that when you design a scheme or an experimental concept, to know what are the possible observable at all. Maybe the experimentalists can get a few, I guess they know everything how to probe these gases. And then how all the work that has been done, and which is massive, a lot of publication on mapping phase diagrams of these Hubbard models. So what's the status? And the part 3, that's my favorite. That's basically what goes beyond Hubbard models. And there you can, all the topological properties will come in, and how we can simulate magnetic phenomenon for neutral atoms. Okay? So this lecture is a gathering of slides, because we have a master lecture with my colleagues Christoph Becker and Christoph Weitenberg. So I catch from some of them the slides, quite a few of mine. So don't. It's a common lecture in that sense. Questions so far? Okay, let's jump in. First part, how to build up the Hamilton operator in the lab. So first thing we need is a kind of a lattice, and that's what solid states are made of, a crystal somehow. And this we do with light, standing light waves. And then we will go to single particle properties and interacting gases. How are the eigenfunction, eigenvalues, eigenstates of the particles in the lattices? Okay, so light waves. Which kind of forces one can exert with light on atoms? So Philippe Courtet did that last week. Some answers.
Radiation pressure and also dipole.
Exactly. Radiation pressure is nice to cool the atoms down, but to make a nice lattice, you don't want to have scattering. So the force we use is so-called the dipole force, which is always in the limit where we are very far detuned from any transition of the atom. So here it's a case of the red detuning for the next picture, but you can also make it blue detune. So the idea was the semi-classical view on how it works is that your light field will induce a dipole moment on your atoms, and your dipole moment of your atoms will interact with the light field. And this is basically here, electric dipole operator, and this is the dipolar Hamiltonian. You have this electric dipole operator, which acts with the electric field. And if your laser light is far detuned, you can see it as a weak perturbation, and you simply apply perturbation theory, and this is the second order term, which is non-zero, the first one. You have this coupling between the ground state, excited state, via this interaction between induced dipole moment and the electric field. Importantly, to notice it's basically scales as the square of the electric field, that's the intensity, and inverse proportional to the detuning. And this is also the same in the lecture of Philippe Corday. It's in the 4th lecture. Everything has been derived already. So you notice here that depending on the sign of the detuning, your atoms will be trapped at intensity minima or intensity maxima. The thing you really need for trapping is an intensity which is spatially dependent, so depends on space. Basically here you can think of a focus like tight laser beam, and this is basically the energy state, how they're perturbed by the laser light, and you see that you have this, where the maximum of intensity is, you have the bottom of your trapping potential. And this makes a conservative trap. You can load atoms in there, just ramping up the intensity of this focused laser beam, but there is no cooling going on. For this you have to act on this intensity. Good. So this is a very nice way of trapping atoms, and when you can make it more quantitative, I've seen that Philippe Corday already introduced this expression of the intensity of a Gaussian beam. That's the only thing you really need to know as laser physicist. This is this exponential of x squared plus epsilon squared over the waste of your laser beam. The waste is varying in space over a scale which is given by the so-called Rayleigh range. So this should all remind you of the last lecture. And if you plug this intensity and this expression for the shift, AC Stark shift of the energy, and make a Taylor expansion, you can get the dipolar potential you are creating for the atoms, and make a Taylor expansion around the center. And you see, because of the Taylor expansion of this exponential, the first term you get is this x squared, epsilon squared. That's always a good sign, because this looks like an harmonic oscillator. And that's why we rewrite all these factors here in trapping frequency of an harmonic oscillator. So having a focused light beam really creates a nice harmonic oscillator. So if you just have one beam, you notice that these two coordinates, they are over the waist squared, and the waist is a small dimension. It's something usually between 10 to 100 micrometer. And the C component scales over this Rayleigh range, which is much larger, over a centimeter or so. This means that this trapping frequency will be high, and this one really low. So you can imagine you have then a cigar-shaped cloud in this kind of trap. You can, of course, use it, but the problem is if you want to cool your atoms further in this kind of traps, which is done by decreasing the intensity of the trap. So you decrease slowly the potential, and then atoms escape of the trap, the hottest one, and then you can cool further. Then the time scale set for this cooling is set by the lowest trapping frequency. So you can never go faster than this lowest trapping frequency, because all this cooling has to do with collision and rethermalization. So you better get a more tight trap if you want to do it. And this is easy, you just have to put a second beam. In the case you have a second beam, the seed dimension, which was only weakly trapped, gets also quite tightly trapped. And then you get trapping frequency typical value can go up to 3 kilohertz or a few kilohertz, depends on how much money you can put in the power of your laser. These traps are not that deep. Even if you have a super laser, typically you get to 1 millikelvin, down to 10 nanokelvin. So 1 millikelvin is quite narrow. So it's hard to directly, after laser cooling, to directly transfer your atoms in an optical trap. Usually you still have to go but in a magnetic trap to make some evaporative cooling, or play other tricks to lower the temperature of your atoms first. And since if you have quite a weak confinement, so a shallow trap in the region of, let's say, 40 hertz, 50 hertz, then you have to pay attention. Gravity plays a role. This is called the gravitational sag. So for the experimentalists who know that, gravitational sag, no? It's a very simple thing. So imagine you have this. Oh, that's really huge. That's not so common. So if I have a trap with this light, very shallow, something like this, it's a harmonic trap, yeah. So here is like the potential, and that's space. Let's call it C. And now if you take the gravity into account, you have something like this. Well, atoms are massive, so you really have to take into account. And that's really comparable, so that the sum of both looks like this. Well, yeah, something like this. So you really have a very shallow minimum here, and it gets shifted. So the minimum of your potential is not there where you expect that it's shifted by up to a few micrometers, so it's not small. Okay, you get really a shift of the minimum. This is what is called gravitational sag.
You have a potential barrier there also?
A potential?
A potential barrier with this tag or not?
Yeah, a small one, yeah. Up to vanishing. But if you want to trap, you have to have a small potential barrier.
No, but I mean with the gravitational sag, does it distortion the gravitational?
So here you mean that they can tunnel?
Yeah.
Yeah. You can adjust it such so that it's been done, but you can also make it large enough so that they don't tunnel. Because at the end of the game, so we want to trap them. But you can also play with it to look at tunneling through this barrier.
So the effective potential that the atoms will see would be that
Tiny thing.
The tiny thing that is crossing the both potentials?
So let me draw it again. So this is the gravity. So it's like simply G in one direction times Z. And you have to sum them up. And if you sum them up, in the worst case, so I made it a bit dramatic, but it's really looking like you have this kind of potential. So you can still trap in there. So around here, it's still harmonic, but the position is not where you thought your waist is. It's shifted by a large amount eventually. So
only in the Z direction.
Only in the Z direction.
And if you put a distorted beam?
You can compensate it, exactly. What we have now is like our beam, they're not the Gaussian beam, but they have different waist, top down and left right, and then you can compensate their ways. But it was just to mention with atoms, one has to care about the gravity with cold atoms. You can find more in these references, so all the references where these topics are properly worked are listed at the bottom. Good. So this is dipole traps. Okay. And now we use exactly the same kind of dipole forcing to trap our atoms in standing waves. So standing waves is quite, you can come to the idea, I guess, that if you have one laser beam, it's still a Gaussian beam, you simply retroreflect it, and as you all know, it makes a nice interference pattern. And in this interference pattern, we trap the atoms. So this is how it's looking like. That's a light potential seen by the atoms, and each lattice side, so you're slicing your condensate or Fermi gas, ultra-cold gas, in such pancakes. If you now add in the orthogonal direction another of this interference set, you get a set of tubes here on the square lattice, so you have nice elongated tubes. And for a three-dimensional lattice, then you get the nice crystal that you know from solid-state physics. So it's pretty simple. This kind of lattice, we always claim they are perfect. Why do we say that? They have no defect, because there is no missing side. It's an interference. How can it be that it misses one of the fringe? There are no phonons, because phonons would be such kind of deformation, right? This is not the case if you have a standing light wave. And typical values, like with up to 30 sides per dimension and 10 to the 5 atoms in there. Yes?
So if you want to stimulate a superconductor,
yes.
How would you do if you have no phonon?
That's true. There is the phonon is not always an advantage. But for the first studies, it was good. But it might be a problem for going further. But there are as well solutions. Good. So, more questions? This kind of course, it's depicted here, basically, since you have Gaussian laser beams, that's always what you send on these atoms, you will also get some harmonic confinement due to the lattice beams themselves. That's why the lattice is not completely flat, but it's curved. This will get important in the next lecture. Good. Oh yeah. So the lattices are perfect, no defect, and I've written here starting from perfect wavefronts. Do you have an idea how perfect it must be? Or how would you build such a lattice? Take the laser and send it onto the atoms, or? No? Usually you have to take a bit of care that it's really a Gaussian beam, so that you want to have a certain mode of the electromagnetic field. So one good trick, to be sure, is to use an optical fiber. A monomode optical fiber will ensure that what is coupled in and comes out is a real TM00. And then you can work with optics afterwards. You're never sure what the laser gives out. Good. Of course, you can do more than this simple retroreflection with a mirror. And a lot of experiments have gone beyond this point. It's just that you know you can aim for a more complex lattices. There are different ideas, of course, because you have a lot of degrees of freedom. One set of realization is what I call super lattices. I hope the whole field calls them like this. It's when you superimpose different lattices. Usually lattice with orthogonal polarization so that they don't interfere, or different frequencies. One example which is very nice, has very nice properties, is like this double wave lattice. It's very simple to get because it's usually done with, you see here all this super lattice here. This is a Kagome lattice. This is a superposition of two triangular lattices. They are made with two different wavelengths here. You see 1064 and 5032 nanometer, and they come out of the same laser. One is frequency double of the other. And then you ensure that they are phase coherent and frequency coherent. And with this kind of lattice, if you control the phase of these two lattices, you can control the relative position, bring these two wells together and apart again. A lot of work has been done with that in the group of Dieter Mischede, for instance. Quantum walks, all this becomes possible with this kind of lattices. You can have optical lattices that have more beam than dimensions. So I explain. In the cubic lattice, you have 3 dimensions and 3 beams. And now the nice lattice we have in Hamburg is a triangular lattice. It's a two-dimensional lattice, but you have 3 beams. 3 beams in 2 dimensions. The good thing is there is this was noticed by Rambert and long ago, 93, that the interference pattern of a lattice resulting from D+1 beam is independent of the laser phase. So if the laser phase of one of the 3 beams is modified, you just translate the lattice. You don't deform the geometry. It makes it very stable, because you always have optic vibrating and all this. And we have used it actually to make nice magnetic fields for neutral atoms. You can use it as a trick. If you put more beams than D+1, you can also do it, but they will interfere, phase will matter, but this brings a lot of tunability in the lattice, and this is, for instance, the setup that Tillmann-Esslinger has, where he has 2 dimensions, but you see there's 1, 2, 3 beams. Let me count. It's a 2-dimensional. But they interfere together, indeed. They don't have any orthogonal polarization, so they really use the interference of all these beams. And you can go from a checkerboard, so like the square lattice, that's more, the minimum are in blue. It's more like a double whale kind of thing. It's a kind of an hexagonal structure. You can go to 1D chains and square, just by adjusting the phase of your laser. So this is really handy, and you can investigate a lot of different systems like this. So why do we continue to make more lattices? One aim is, of course, to getting closer to the complexity of solid-state crystal, because so far it was more like we had the cubic lattices. And you get new physical properties. So as soon as you have this, these super lattices, you get direct points. You can get what one calls flat bands. I will explain today what it is. It's really new physics coming in. You can also plan to use it to have new probing protocols to probe your gas. So use some degrees of freedom of your lattice to get more information on the system. So the list could be much longer, and it's getting longer and longer, but I don't want to list all of them. Just be aware there's more than square. Good. Now let's go into the old memories of solid-state physics, Bloch theorem and Bloch functions. You all know that? You didn't remember? Okay, let's make a short overview. What is the Bloch theorem all about? It's super simple. The idea is it describes non-interacting particle in an optical lattice. So it's easy to write the Schrödinger equation for the system. It's like, let's say 1D for the start. This is the kinetic part of the Hamiltonian, and you have the lattice part. Okay, V von x. And you have your wave function. That's what you are looking for. You're looking for eigenvalues and eigenfunctions. So this potential is periodic in space with a certain lattice vector, A. And of course, this periodicity in space will result in a periodicity in momentum space. You know, real space, momentum space, and simply a Fourier transform. And therefore, the reciprocal lattice vector is like 2 pi over A. Like always for Fourier transform, have the 2 pi in there, and everything will be fine. And then it's actually quite easy to guess, or what the Bloch theorem is all about, is the solution will look like this. They will look like, they have 2 indices here. One is the quasi-momentum, because due to the periodicity in space, and the one in quasi-momentum space, you can restrict everything for quasi-momenta between minus g over 2 and plus g over 2. That's called the first Brémond zone. And you will get some bands. That's the index n here. And then you have an exponential factor with the quasi-momentum k in, and this so-called cell periodic function U von K and N, which are periodic in A. And the spectrum will look like this, so this will go through. The aim is to remind you how this comes all about. And this are the so-called bands you get, and you have these band gaps between the different bands. And that's the energy spectrum given by the Bloch theorem. How to get the eigenvalue and the band structure. Eigenvalues are the energy, that's the band structure. As an experimentalist, you want to calculate it for your particular wavelengths, waste, etc. That's a good thing to do. It's not super complicated. So the first good idea is this equation, obvious solution or plane waves. Plane waves with the periodicity of the lattice. So a good thing would be this unknown wave function to write them in the basis of these plane waves. And this is what is done here. So we just write that this wave function, we can expand it as a Fourier sum and discrete plane wave with some coefficient, Ck, and I have defined some dimensionless quasi-momentum, just that it gets shorter in there. And this Ck from n, they have two index, the quasi-momentum and the band, are called the Bloch coefficients. So the same thing you have to do. So we have expanded now the wave function. Now we have to expand also the potential in plane waves. This is done here. And then you plug everything together, as usual, for Fourier decomposition. And then you can always identify the terms which have the same exponential in there. And then you have a nice compact equation in quasi-momentum. And this is an eigenvalue equation for the coefficient. Here I've defined, that's a very important scale. I will only speak in recoil energy. What it is, this recoil energy is basically the energy one atom gets if it absorbs one photon from the lattice. And that's the right energy scale for the description of all this physics. It's usually something like a few kilohertz in terms of frequency. So this you can just rewrite as a matrix. This is basically all this equation is written here. Maybe we don't dive too much into the detail. You can read it home, and if you have some trouble, we can discuss this tomorrow. This coefficient here are the decomposition of your lattice potential. Don't panic. This is super simple to know which value they have. You can make a Fourier transformation of your potential, but basically they only have, for one-dimensional lattice here, you see there are only terms which are off diagonal, the first off diagonals lines. And this is easy to understand from the view that the optical lattice will couple plane waves that differ exactly by 2 times the lattice vector. And why is it so? You still have your 2 beams coming on your atom, and they can basically absorb one photon from this one beam and emit in the other beam. So the only way your optical lattice can change the momentum is by absorption and emission of the photons, and that's why you have this 2KL, and that's why you have only this off-diagonal terms. And then, once you have this matrix, you simply ask MATLAB to diagonalize it, and you get eigenvalues. That comes really directly out from diagonalizing the lattice. It's not complicated. And here, you have these different lattice depths, and you see you have this lowest band, first excited band, etc. And as the lattice gets deeper, these bands will get flatter, and the band gaps will open. Good. So this is how to get this band structure. So it's a very important information, but that's only half of the information. Now we would like to know what are then the eigenvectors. And the eigenvectors are this so-called Bloch coefficient. I rewrite how we have expanded this function in Fourier, the discrete Fourier expansion, and this coefficient, they are also there. So if you diagonalize your matrix, you also get the eigenvectors, and you can plot them. So just for you to get an idea, what is here. So this is actually the form of our eigenfunction in momentum space. These three plots here, therefore n equals 0 is the lowest band, and quasi-momentum 0. If you remember how the bands are, and they are here, you see that's the minimal energy point. And that's how it looks like. So for shallow lattice, middle, and deep lattice, what you see that it broadens in momentum space. It makes sense. For a weak lattice, you have basically like a free particle. Let's say it's really super small. So you expect only one quasi-momentum here, 0. And for deep lattice, you have many momenta, which means you're delocalized in momentum. You get localized in space. So deep lattices will indeed pin your atoms at sites. So you always to have, with optical lattices, to think in real space and momentum space and make this Fourier transform to see in which regime you are working. So here, the localized in momentum space means it will be localized in space. Maybe one interesting thing to go beyond, but the easiest solution, you can also have a look at the wave function for quasi-momentum pi over a. So that's here. So the same thing then for quasi-momentum 0. When the lattice deepens, then it broadens. Makes sense. You see here that you don't have only the quasi-momentum -1, which is basically minus pi over a, but you also have a strong contribution of a quasi-momentum 0. Don't panic, that's not wrong. That's correct, because you have to think in terms of quantum mechanics. So the expectation value of your quasi-momentum is always quasi-momentum times, so the value of the quasi-momentum times the probability to get it. And this makes 0. And this makes the value you expect, okay? It makes all sense. Good. An important thing to notice, because it will be important in the third lecture, for this quasi-momentum pi over a now, if you think in real space what it means, so if you tunnel from one side to the next, you can make here x becomes x plus a, and what will come out of this resummation, or if you will have a lot of exponential coming out, is simply that you will have an exponential of I pi. So it means that the wave function acquires a size of pi. So if you tunnel and you're sitting at a quasi-momentum which is finite, you will always acquire a finite phase. If you tunnel from a quasi-momentum 0, then it doesn't matter. The phase is always the same. Okay, thinking in terms of spins, for instance, yeah, you have a certain orientation or a certain phase at the first site. If you sit at this pi over a, the next one will be like this and like this. So you have a staggered phase on your superfluid. This is a very interesting point to work with. You get more interesting superfluids. Good. Here you see, and you will see it very often in the next slides, that figures are taken from the Cours du Collège de France from Jean Dalibard. So it's in French, but most of you can Portuguese and Spanish, and that's easy for you. So you can find all this lecture from Collège de France on the website of Jean Dalibard, and I really encourage you to read them. There's a lot in there. Take the time, and that's really an excellent lecture. And you will learn French. Good. Okay, now we have eigenvectors, Bloch coefficient, so you remember the Bloch theorem. Basically, we are building up this Hamiltonian. For now, we have the single particle properties. So it's time to put more than one atom in there. I would say. Let's see. Let's put some atoms. So what about quantum statistics? Who can tell me what is a kind? This is the energy spectrum. We see that for deeper lattices, these gaps increases. Remember that the wave function localize. Bosons, how is it looking like in this band structure? Where are they sitting? In the lower energy, that sounds good. All of them. So it means in the lowest band, quasi-momentum 0. That's a correct answer. So here, statistic matter. So if I have boson and this band structure, so it looks like super flat, but okay, yeah, I make it like this. They are all here, quasi-momentum 0, energy. So, and what about fermions? So they see the same band structure. What happened with fermions? Up to the Fermi energy, very good. So they can't occupy, so they are spin polarized, they can't occupy the same quantum state, Pauli principle. So you have to basically fill up your band. So the first fermion sit here, and then the next one sit next to it, and then you fill up to the Fermi level. So you can also start filling this upper band, and somewhere you have this Fermi level. So for the ground states of particles, quantum statistic matters. So if you pour bosons or fermions and lattices, the physics you will look at will be pretty different. Good. What about the interactions? So they were all non-interacting still.
For bands, it's dispersive, the interactions will not matter, but if your band is flat, the interaction may play a role.
I completely agree. In flat bands, interaction play a role, but they play a role as well, even if you have a strong dispersion.
Yeah.
Or let's put it differently. Which kind of interaction do we have in ultra-cold gases? So for this atomic gases. Van der Waals? It's a very local one, except if you have dipolar atoms. But otherwise, for all other people, you can really take it as an extremely local, let's say, point-like interaction. Okay, that's a point-like interaction. So how do we put this together with this kind of Bloch states? They are very nice, and they're easy to calculate. However, they are fully delocalized over the lattice. How can I describe now the interaction between waves? You see the problem we are facing. Interactions are not easy to bring in agreement with this Bloch wave functions. So we would like to have something like the interaction will be on the lattice sides only on a single lattice side. So the interaction between lattice sides you can usually neglect if you don't have dipolar interaction. So we would like to have something like this. So I've drawn these bands here, but we still have no definition of the tunneling, and we don't know how to explain the interaction in these Bloch wave functions. It looks like we didn't take the right description, right? This is then this model, which I will derive now, is called the Hubbard model, and it's very close to the description of solids. The point is the ions creates deep potential. Your electrons are delocalized eventually, so they can hop from one ion and crystal to the next ionic potential, and they interact together, of course, and our atoms will do more or less the same. So they are delocalized. So we would like to know what kind of hopping, what kind of on-site interaction we have, but with this Bloch formalism, it's not so easy. And that's why this part is called Wannier function and Hubbard model. So we need a new basis to describe the physics in a more local manner, because our interaction are local. And this is not so long, so it's just a summation of Bloch function that we have already calculated. So this Bloch function, they were very handy to calculate this band structure. They are completely delocalized over the lattice. This we have all discussed right now. Is this interaction or local? We would like to have local wave function. So how to get local wave function? If you have a set of Fourier waves, of course, you sum them up, and you will get wave function which are localized at a single site. They are called Wannier function. It's really maximally localized to individual lattice sites. And here is how you calculate it from our good old Bloch function. N is the band index, K is the quasi-momentum. It's a simple summation, and you have the inverse transformation, of course. So I've plotted them just for you to get an intuition how it looks like. The very funny thing is you can calculate all this with not a lot of efforts, and that's exactly what your experiment is doing. So this Wannier function, that's how they look like here for different lattice steps. So it's increasing from left to right and to the bottom. So here is a weak lattice. You see that this wave function has wiggles which are not zero. So it really is present on the other lattice sides. It's non-zero here, left and right. What is in dash blue is basically the Wannier function on the neighboring side. And you see that they have overlap. That will be important in a second. And if you increase the lattice, then you see that this Wannier function, they're really strongly localized. So it means your atoms gets really, the wave function gets pinned on the lattice side, and then there's almost nothing leaking to the next side. If you calculate the overlap between two Wannier functions, so I mean intuitively you know that that will be the tunneling. The probability from your wave function to get from one side to the next will be dependent on how much overlap you have between these two guys. So here, 0, here, non-zero. Tunneling will, of course, be much stronger for shallow lattices.
So the Hubbard model will work only in this last case?
Yeah, that's my next slide.
Okay.
If you wait a second, and then you can ask, of course, if it's not enough.
Sorry.
And then and they are, because I love higher bands now, just because it's fun, you can also plot them in higher bands. Not everything is occurring in the lowest band. Then they are orthogonal to each other. And this is the Wannier function in blue of the lowest band. It's a boring Gaussian-like wave function. And if you go to the next band, then you will have a node. Yeah, this is like in a harmonic oscillator. You have this ace-shaped wave function at the lowest orbital, and then if you go higher, you get this P-shaped orbitals, and then higher and higher it gets more and more fancy, and that's how you can get this in a hexagonal lattice. Now, this is nothing that the picture you have seen during the advertisement is nothing than just a calculation of this Wannier function for higher bands and fancy lattice geometry. Good. Now, tunneling. Finally, I define the tunneling, and then I will go to the interaction. So I don't know much time do I still have time, right? Yes. Like 20 minutes. Good. I think I won't fill them all up, but let's see. So how to define the tunneling. So I told you already at the end of the story, this will be the overlap of two neighboring Wannier function. But if you want to do it more systematically, it's actually pretty simple. So here is our Hamilton operator, since we have diagonalized it with the Bloch function. You can rewrite it like this. This is an eigenbasis. Eigenvectors, eigenenergy, it's a diagonal matrix. And you can introduce then creation and annihilation operator for particle in the Bloch wave with band index n and quasi-momentum k. This is basically creation annihilation of a particle in a certain Bloch wave function, and this is completely equivalent. Just to writing or compatible. And from this annihilation operator for particles in Bloch waves, you can define an annihilation operator for particles in Wannier function, the one which are localized. And they're a very simple transformation. It looks like a Fourier summation, of course, like we did with the function. And using this kind of expression, you can rewrite this Hamilton operator in terms of annihilation creation of particles in Wannier function. And basically, you can read then, this is a big matrix. And you can read off the elements of this matrix and see, is it diagonal? If not, what is the coupling element between my non-diagonal elements? And this, what is called here, Jn, J minus J prime, this is the index for the sides. So it's between side J and side J prime. This is the matrix element coupling to Wannier function, and it has this kind of expression. So here, for simplicity, I just write J, put J prime to 0. And this element couples the Wannier function for a quasi-momentum 0, for lattice side 0 to the Wannier function to lattice side J with our favorite Hamilton operator. So this is easy to calculate if you rewrite it like this, because this energies or the band structure you have we have, and you just have to sum up some exponential together, and then you get all coupling elements, so you can get the complete matrix. So the hopping amplitude, as I said, is really given by this overlap between the two Wannier functions. Here it's from side 0 to side J. And for increasing lattice steps, we have seen that this Wannier function will really become more and more and more localized. And therefore, this hopping amplitude drops exponentially. Here again, as this plot here, remember, and even if you look only at the next neighboring side, so this is plotted here, this is for j equal 1, meaning you go from one side to the neighbor, j equal 2 sides apart. How much is the tunneling? 3 sides apart. And you see that for deep lattices, they all go to 0. But also for moderate lattice depths, you can really safely neglect hopping to the next neighbor. Okay, it's cold atoms and optical lattices are perfectly described simply with next neighbor hopping. And that's really comes only from this calculation overlap. You plot it and then you're convinced that you can drop all of that coupling. Because otherwise the matrix is really complicated because you really couple every side with the next. But all these terms are super small, as I hope, convinced you. And then you're really now left only with, again, a matrix with only one left and right diagonal. Again, if you want to know more, it's all in the lecture at the Collège de France. Good. So it means now we go to the Hubbard model, and there are two hypotheses. One I have just explained. We just take into account only the next neighboring hopping j. Yeah, that's really to the next side. All of the other, they really vanish. And we restrict everything to the lowest band. This is basically because the band gap are quite hard to overcome if you don't do anything. So if you prepare a ground state, then you're never in higher bands. To go in there, you have to disturb the system a bit. Okay, so it makes actually this big Hamilton operator I had here with a lot of elements, so all bands and all sides j and j prime. This was a huge matrix. Suddenly it collapses to something much easier, which is like this. You have only hopping between one side to the next. And you forgot about the band, we just restrict ourselves to the lowest band. That's why n index is no longer there. That's what is called Hubbard model or Hubbard Hamiltonian, and that's where it stems from. So from all this calculation, Vanier function, etc. There, it's possible to calculate the dispersion relation. So it's the energy of the system as a function of quasi-momentum. So the way you calculate it, if you have this Hamilton operator, you just squeeze what you want as the expectation value of the energy. And this is what comes out. It's minus 2j, and you have a cosine of r times k. So here they are plotted, basically. This is for a shallow lattice, so you see more or less the form of this cosine. And it's still there for a deep lattice. But then j is strongly reduced for deep lattice. That's why the width here is super small. So you can really read off from the band structure the width of your band gives you really the magnitude of your tunneling. That's directly related. So it's given by a certain number of j. Don't be mixed. It's depending then if you have a 1D, 2D, 3D matrix or lattice, you get different numbers of j. This is simply because you have a sum of cosinus along x and y and z, and then of course here it can only go to plus and minus 2 because cosine only gets to plus and minus 1. And then if you have two of them, then it's more and more and more. Important thing, just the width here is proportional to your tunneling. And you can even make an approximation. So if you don't want to calculate your tunneling via this formula, where you have nicely calculated the Vanier wave function and you calculate the overlap, there is an approximation which is very useful. You can simply approximate your Vanier function with Gaussian wave function. It's not completely true, but I mean the deviation here is small. So for deep lattice you can do. Here, of course, you might be disappointed a bit. But for deep lattices, you can simply say, okay, my Vanier function is a Gaussian with a certain width, and there is this formula. I will add here, this formula comes from an important paper by William Zwerger. I guess all experimentalists use it to get an approximate. Importantly, you see that this tunneling decreases exponentially with the lattice depth. So this means this is quick. You change a bit your lattice depth by changing the intensity of your laser, and you really suppress the tunneling a lot. Good. Well, tunneling we have to continue. We still need 10 minutes to get the interaction out of this model. Hold on. Good. Exactly, interaction. As I mentioned, so far I didn't write any Hamiltonian describing the interaction. That's the first slide. So you can describe the short range interaction of strength J. They're described by a pseudopotential. This pseudopotential is really like a delta potential. I guess, Jörg, you have introduced all of this. Mm-hmm. Not the pseudopotential, okay. So you have this field operator, and always this interaction has to do with this psi at a position, psi at a second position, and then psi dagger and psi dagger. Since the interaction are point-like, that's why they all have the same index here, all x, because interaction only occur on site. There is no way they can interact at the neighboring site. So if you now simplify, because this is still the description including all bands and all sites, then you can make it much simpler, just restricting to the lowest band and nearest neighbor coupling. And this is the kind of Hamilton operator you get. So I think it's important to understand this guy, of course. This is something which has to do with U. So U, what it is is basically given by the interaction strength of your atoms, and this Wannier function, an absolute square is missing, so the absolute value is missing, of course, absolute value to the power of 4. So it's the overlap, so you basically, the more localized your Wannier function will get, the biggest U you will get. And if you approximate this Wannier function by a Gaussian function, this makes it much easier, and then you see that this gives an analytical expression. Again, it's in the paper by William Zwerger. I will add it at the bottom, which is pretty simple. It's all analytic. You see that it's some factors. K is a lattice vector, A is a lattice spacing. These are the lattice steps, and it scales not so impressively with the lattice steps like the tunneling was doing. And the tunneling was really exponentially scaling with the lattice steps. Here, it's only a 3/4 power. So you don't do much on the interaction by simply tuning the lattice steps. Good. So this U is basically a measure of how localized your wave function is, how tight the atom have to be. This is the price you have to pay. And now if you put two atoms on these sides, you know this operator, no? This number operator. Of course you know it because Michael Brun was using it for photons. Yeah, it counts how many atoms are there. So if I take the example of 1, then I have 1 particle minus 1, it makes 0. That's a good news. 1 particle alone don't pay any interaction on the side. So now if you have to add a second one, then this number operator will give you 2, minus 1, it's 1, times 2, U over 2, it gives a U per particle. So if you now add another particle, it doesn't give U per particle, you really have to have this N times N minus 1. So this is basically the picture I promise you we will at some point arrive at. We have some atoms, they're really up only from one side to the next. This grayish part means that they are only in the lowest band, and they can interact only on site. Okay? And the description for spin 1.5 fermions is pretty similar. For fermions, it's more complicated. Why?
Because of statistics.
Of statistics, exactly. So if you have spin polarized fermions, they can't, because of Pauli principle, they can't be on the same side. So there you don't have to look at the interaction. But it only is easy to describe if you have two spin states. Then they can be on site and they can interact. Okay? That's why you have here this new index coming up with the fermions up and down, like for electrons. Good. I don't remember how many slides I still have. 20 minutes? No, I will be, I think I'll make 2 slides and then I'm done. Let's see. So just a short summary where we are, okay? I hope I convinced you that the Hubbard model is a very good description of ultra-cold gases and optical lattices. For bosons and fermions with spin 1/2, now we can write it in this form. This or creation annihilation operator, bringing one atom from one Wannier function to the next. They interact on site. Looks super simple, this possible Hamiltonian. And these parameters, J and U, they can be tuned using the lattice steps. And this is important because this Hubbard model we will look in a second at the phase diagram of this Hubbard model. Of course, depending on the lattice steps, you will get very different states. And just for you to get a scale, if now one plots the ratio U over J, right, from this analytical formulas more or less, you get 4 orders of magnitude. That's the range over which we can really tune or set this parameter. So it's a very big, 4 orders of magnitude is a really large range. And this we can be really done extremely precisely, as you know. The question now is, okay, we have this model. Do you know anything about the phase diagram of this Hubbard model? Phases for bosons. Someone? No?
For depends of dimension. For 3 dimensions, at U smaller than U, critical U, you have metal, and U bigger than critical U, you have a multi-insulator, and you have magnetism if you go outside with.
That's good, yeah.
What?
That's correct, indeed. For fermions, you even get magnetism.
Yeah,
For bosons, then you only get what you were calling a metal and an insulator. We call it superfluid and mod insulator, and that's pretty much the same objects. You can guess, you have 2 terms in your Hamilton operator. They will compete. So depending on the ratio between the tunneling and the interaction, we get 2 phases. That's the usual part. So it's a first quantum phase transition. That's the thing I wanted to mention. And depending on this ratio, you expect different properties. What is my next slide here? For bosons, it's easier because then you don't have this extra spin to care of, right? This is for the next lecture. You have 2 possible phases. The superfluid phase, where you have weak interaction, large tunneling, so the lattice is not deep. Your atoms are really delocalized in space, and means localized in quasi-momentum, right? They are well described then by Bloch function there. And this is like a boson-Stein condensate in the lattice. This is what is depicted here. All your boson are at quasi-momentum 0. Like, they don't see that there is a lattice. You could put them in a dipole trap, more or less. It's more or less the same. They do see that there is a lattice. I will show you this next week. Now, if you have a deeper lattice, at some point you suppress the tunneling so much that particle localized. So they are pinned on this lattice sites. But it's not as simple as that. The particle, now the energy scale which is important is the interaction. To get the ground state, you have to see, then atoms have to organize to pay as little interaction energy as possible. And this is what you get, for instance, in this configuration where you have only 1 atom per lattice sites. Yeah? If they would like to tunnel, then the interaction energy costs so much that it is an excitation, actually, of the state. So this state minimizes the interaction part, and there is a strong localization of the particle. And this means that there is a reduced particle number fluctuation. I will explain in a slide. And this is a lot to do with Michel Brun. What Michel Brun was mentioning this morning, it's really like a number state. And this is more like a coherent state, like for photons. And this, solid state physicists call this a metal, and this an insulator. But we speak about that's the same objects, and they are incompressible like insulator or in solid state physics. Good. What are the properties of these phases? Superfluid phase to start with, so that's the one where atoms are completely delocalized. They're this very localized in momentum state. So it's the wave function, the first guess. It's quite easy to write. I simply write that I put all my atoms, n is my atom number. I create all my atoms at quasi-momentum 0. And that's pretty much it. You have to take care of the normalization, and that's the wave function of the superfluid. Pretty simple. Then you can rewrite it in the Vanier biases, of course. Then they occupy all sides. And why is it interesting to do so? It's because then you can look at properties of the state. And if you look in this kind of basis change, you see that this state is a kind of a coherent state at each lattice site. So at each lattice site, you can have 1 or 2, 3, 4, 5 atoms. It's a discoherent state. The square of the coefficient follows a Poisson distribution, exactly the same as in the cavity by Michel Brun. Okay? This is the kind of result for n equals 1, for the mean value, or 5 or 9, and you see that they get shifted and follow a clear Poissonian distribution. So if you had to count the atom number on your lattice, if you freeze the system and look at it, you will get many times, let's say, you will get this Poissonian distribution at each lattice site. And this is possible to do, I will tell you next week. This has been measured. Okay, this is maybe not so important. So superfluid state, remember, it's a condensate state, quasi-momentum 0. It is a Poissonian distribution for the atom number per site. The Mott insulator is named after a Nobel Prize winner in 1977. So that's a description of what they call atomic limit. It's a solid state physicist. So when electrons don't tunnel, they're on atoms. So they're on the ions and it looks like an atom. It's neutron. That's why they call it, that's the atomic limit. And repulsive U, he actually demonstrated that the ground state, if you can do so, if you have a mean particle number per site of 1, you have 1 atom per particles. This cost in energy 0. Yeah, and if you have more atoms, of course, at some point you have to put 2 atoms per lattice sites, because your lattice is not infinite. So at some point you really have to resign and say, okay, it's more like 2 particles per site, but exactly 2 on each side, and this costs an energy 3U. And the fundamental excitation from this ground state, you see it's, in case an atom would like to tunnel, then it has to pay this interaction energy U, because 2 atoms are now on the same side. So this means that this ground state, if you prepare it, you can also check that the excitation spectrum is gapped. Because if you excite your system and you don't bring this kind of energy, U, it's a kilohertz basically, you will never make an excitation. You have to really reach U, and then you see, okay, now I start destroying the system. And this has been measured as well. This is doable as well with cold atoms. So this kind of state, superfluid and Mott insulator, you see they have very different property. Here I told you it's a coherent state on each lattice sites. Here it's a number state. It's really like I have 1 atom or 2, no fluctuation. And exactly, this is the phase diagram, and the measurement of all this we will just discuss next week. But just a last comment here. This is a mean field phase diagram. So of course, if you look in details, there are some deviation, but it's actually quite simple to understand. It's a J over U. So when it's large, it means I have a large tunneling. Then I have a superfluid phase, where atoms are completely delocalized. And as I reduce J, or increase U, you can choose, at some point I enter in this one lobe here, which is called a Mott insulator lobe, with a certain number of atoms per site. Okay, it says it's an abrupt transition here. And this second axis is important to take along. What is mu? Usually, it's always the name of chemical potential. This is the chemical potential. It tells you basically how many energy it costs to add or remove 1 particle in your condensate is a measure of how many particles you have in your condensate. So if you increase this mu, then you see more of this Mott insulator lobes, that's how they are called, and they're the lobes with 2 atoms per side, 3 atoms per side, etc.
For repulsive
Interactions.
boson.
Yes.
Okay.
No, otherwise the phase diagram is more spectacular. We will do it next time for fermion, and it has more phases. But we started with bosons.
Okay.
Because it was easier to get in the lattice. I will explain why it was easier to get the first results with bosons. So this phase transition has been really intensively studied. It was a hallmark of the whole cold atom community. This is the next lecture tomorrow. You have to come back because there we'll get all the nice pictures. I will show you what has been all measured in this phase diagram, how it is mapped, or how sure we are of every details. So for today, I will stop here. I hope I convinced you that the standing light waves are a good way to model this Hubbard, or to make a cold atom simulator for this Hubbard model. It was not so fancy. I could have shown you a nice picture earlier. That's easy, there are so many. But I wanted you to understand what is measured. And that's why we had to go through this Bloch functions, Wannier functions, and all this, because this will matter next week when I will present you how we read out the state of the system. What are our methods, and what are the challenges, etc. There you will see 1,000 of nice pictures. And again, to advertise by part 3, it's like a bit beyond this Hubbard model, how to add new properties in this Hamilton operator. I hope to see you tomorrow then. More questions?
Could you explain again how to break that nice harmonic oscillator potential from the laser?
From the laser?
Yes.
At the very beginning?
Yeah.
You mean the dipole trap or? Okay, which part? Let me see. I don't remember. It's quite far. Was advertising a lot? Oh, my PowerPoint file is much too big. Let me see. I want to save. In a second, I might be ready. Now. Excellent. Here? So do you want to get the semi-classical view, or what was the idea here is to calculate the Stark shifts, and this you can do in a semi-classical view. Semi-classical means that your atoms is quantized. That's what you see here. Oh, I didn't tell everything. That was a bit the warming up. Huh? So you have your atoms is quantized. It is a ground state and excited state. The light field is classical. You see, we write a magnetic electric field A, and the interaction is due to the fact that your electric field of the light will induce a dipole moment on your atoms. Usually in the ground state, they have a zero dipolar moment. And this dipolar electric dipole moment here, minus A, the charge of the electron, times R, the position of the electron, will interact with the field, like a dipole with an electric field, with this interaction here. So if your perturbation is small, so if this perturbation operator here has a small influence, and you know from perturbation theory that we are all speaking about big matrices, and don't believe that you just have to make an approximation of this value. You really have to look at the matrix and how big are the off-diagonal elements. But if this is small, then you can use perturbation theory, and this is the second order perturbation theory. You usually get the coupling from the ground state to the excited state with your perturbation operator here. That's the coupling amplitude, so it's a scalar product, square over this electric field square. Okay? This is clear? So it's super easy to calculate the Stark shift like this. And then you can use classical formula for this dipole operator. They are given in this paper here. And this gives you a bunch of pi and c square and omega 0 to the cube. And that's the exact expression of the light shift you expect at a certain amount of light, which is given by the intensity I here, over the detuning. So now if you want to trap something, you don't need only a shift, you need a potential landscape to make a trap, an harmonic trap. And that's why the trick we play is to let the intensity vary over space. And you can do it very good if you have such a Gaussian beam. And then you have the intensity which rises and then decreases again. And this makes a very nice harmonic potential. Yeah? And this is easy to calculate. Here, this intensity is known for a Gaussian beam. And this is given by the Gaussian profile of a laser beam. You can check it on Wikipedia. Just put it in there. It's, of course, depends on the power of the laser, the waste. And if you put this in the formula and make a Taylor expansion around the center, because it really looks like an harmonic oscillator, then you will see these terms with x squared, epsilon squared, z squared appear, and then you know how the trap frequency will be. Okay, and whether they depend from the waste or from the Rayleigh range. But it's very well detailed in that publication. Yeah?
What size typically is the lattice constant of this?
Very good question. I was hoping that someone asked because I completely forgot to mention it. Thank you very much. So here it's all done by light. I will discuss this point more next time also. So it means visible light up to infrared, more or less. So it's the lattice spacing, since it's an interference pattern, it's lambda over 2. And lambda is between 400 and 1,000. So it's 500 nanometer. Much larger than what you have with solid state sample, of course. And that's good because you can even resolve single side. It's hard, but it's possible with optical lattices. Yes, it's exactly the same. So basically one beam and you have the tweezer. Yeah. The problem with the tweezer is that we really have a low trapping frequency here. So if you want to move something with it, you have to not to be too fast. But it's possible to transport cold atoms. In one of my setups, I transport them like over 30 centimeters with a tweezer. This works super nicely. Just a lens on a translation stage, and you move it. You move the waste over 30 centimeters, a cold atom follow. More questions?
So you start with a cold atom cloud, you then turn on
the lattice, yeah.
The lattice. And can you have just one atom in the lattice, or when you turn it on, you will have?
One atom is hard. Usually we have sample of 10 to the 5 atoms, more or less, because it's easier to detect.
Just one atom per site.
Per site.
No, just one atom.
Okay, one per site. Okay, that's easier. Then you really have to control the atom number very well. That's not so easy. But it's maybe not, so in some part of the lattice that would be the case. That's a very good question I have here in the last slide. This phase diagram. Yes, so in a lattice, usually if you do it the standard way, not the complicated way, I told you they are curved, our optical lattices, because of the Gaussian profile of the beam. So they are not flat, but it means that the chemical potential will vary in space. So imagine you have one state in the trap, the maximal chemical potential is at the center, and then it will go to 0. And if we probe all this kind of phase diagram, then we always have a cut, because we always go to 0 at the edge of the cloud, and then actually basically get a cut through this phase diagram. So we have, depending on the atom number, up to n equals 3 atoms at the center, and then you get so-called wedding cake structure. You have n equals 3, and then n equals 2, and then 1. This way we'll discuss more in the next lecture. We always have a cut, and to get only n equal 1, then you have to have a quantum gas microscope. Or select very carefully a certain part of your lattice with optical mints, holographic mints, but it's really hard. But I will tell more tomorrow on that. Good. Then it's time for lunch, no? Yes. Hi.
Thank you very much. It was really good. And so
Thank you.
I want to ask you why the interaction energy increased when you increase the lattice
Depth.
Yes.
Oh, because they get more and more squeezed. So you have to imagine if you have two atoms.
So the overlap between these two.
Let me switch this
will
off.
be bigger.
Yeah, exactly. So that's why it's scaling.